late summer, 1943. The port of Norfolk, Virginia hummed with an industrial rhythm that seemed impossible to German eyes. Oberingenieur Friedrich Müller stood on the viewing platform of the Newport News Shipbuilding facility, his engineering credentials from the Technical University of Berlin meaning nothing now except that the Americans wanted his expert opinion on what he was witnessing. He had been captured in Tunisia 4 months earlier, processed through the prisoner of war system, and now found himself part of a carefully selected group of 32 German engineers and technical specialists brought to see American shipbuilding operations. The Americans called it intelligence gathering. Müller called it psychological warfare of the most devastating kind. What caught his attention first wasn't the scale of the shipyard, though that was overwhelming enough. 8 Liberty ships in various stages of construction stretched across the facility, each one a monument to American industrial capacity. What stopped Müller cold, what made his engineering mind rebel against the evidence of his own eyes, was the welding. Specifically, how fast it was happening. A welder was working on a hull section perhaps 50 yards away. Müller watched the man move along a seam, the welding torch leaving a perfect bead of molten metal in its wake. The welder moved smoothly, continuously, without pause or hesitation. The seam was perhaps 20 feet long. Müller had timed welding operations hundreds of times in German shipyards. A 20-foot seam of that thickness should take a skilled welder approximately 40 to 45 minutes to complete properly, accounting for setup, multiple passes, cooling time between passes, and inspection. This American welder completed it in 7 minutes. 7 minutes. Müller checked his watch again, certain he had made an error. He watched another welder begin a similar seam on a different section. 6 minutes, 30 seconds. A third welder, working on a bulkhead plate. 7 minutes, 15 seconds. The consistency was almost more disturbing than the speed itself. These weren't isolated instances of exceptional skill. This was standard operating procedure. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Hauptmann Klaus Dietrich, a naval engineer who had overseen U-boat construction at the Blohm and Voss shipyard in Hamburg, stood beside Müller with a face drained of colour. "That's impossible," he whispered in German, knowing the American escorts wouldn't understand. "The metallurgy doesn't allow for it. Welding that fast would create weak joints, thermal stress, incomplete penetration. Those seams would fail under load." But Müller had already moved past denial into a more terrifying realm of understanding. The Americans weren't violating metallurgical principles. They had somehow transcended to them. Or more accurately, they had developed techniques that rendered German welding methods obsolete in the same way that automobiles had rendered horse-drawn carriages obsolete. The comparison wasn't just apt, it was exact. German shipyards were using horse-drawn carriages while Americans drove automobiles, and both sides had somehow failed to notice this disparity until the race had already been lost. Their escort, a cheerful shipyard supervisor named Robert Morrison, noticed the Germans' confusion and mistook it for professional interest rather than existential horror. "Impressive, isn't it?" he said, his voice carrying the casual pride of a man showing off a well-maintained lawn rather than a revolution in industrial technology. "We've cut welding time by about 75% compared to traditional methods, changed everything about how we build ships." 75%. The number hit Müller like a physical blow. A reduction in welding time of 75% didn't just mean ships were built faster. It meant everything was built faster. Ships, tanks, aircraft, bridges, factories, everything that required metal to be joined to metal. Welding wasn't some peripheral technology. It was foundational to modern industrial production. A 75% improvement in welding efficiency translated directly into a 75% improvement in overall production capacity for virtually every piece of military equipment. The mathematics were devastating. If American welders worked at speeds 3 to 4 times faster than German welders while maintaining quality, then American shipyards could build 3 to 4 times as many ships with the same number of workers, or the same number of ships with 1/4 the workforce, freeing the remaining workers for other war production. The strategic implications expanded geometrically. More ships meant more supply capacity, more troop transport, more naval power projection, more welders freed for. Other work meant more tanks, more aircraft, more artillery. Germany had entered a war against an opponent that could weld 3 times faster. No amount of tactical brilliance or operational excellence could overcome such a fundamental industrial advantage. Morrison continued his explanation, oblivious to the psychological devastation he was inflicting. The key was solving the electrode problem. Traditional welding electrodes required constant stopping and starting, changing electrodes every few minutes, letting the metal cool between passes. Real bottleneck. But some folks figured out how to make continuous feed electrodes that could run for extended periods without interruption. That, plus some innovations in flux composition and arc control, and suddenly you could lay down beads 3-4 times faster than before. Müller forced himself to ask the question, though he dreaded the answer. When did you develop this technique? Well, the basic research started in the late 1930s, Morrison replied, checking a clipboard he carried. But the real breakthrough came in early 1942. A fellow named James Meredith worked as a welding supervisor at one of the smaller shipyards on the West Coast. He was frustrated with how slow traditional welding was, started experimenting with different electrode compositions and feeding mechanisms. Took him about 6 months of trial and error, but he figured out a combination that worked. By mid-1942, his innovations were being rolled out across all major shipbuilding facilities. Early 1942, while Germany was still celebrating early victories in Russia, still believing the war was winnable, American welders were already developing techniques that would make German shipbuilding obsolete. The disparity wasn't just about resources or production capacity. Americans were innovating faster, solving problems more creatively, implementing solutions more efficiently. They were operating in a different industrial paradigm entirely. The group moved deeper into the facility, passing workstations where welders, many of them women, operated with practiced efficiency. Müller noticed the equipment they used. The welding machines were compact, mobile, easily repositioned. The electrode feeding systems were elegant in their simplicity, requiring minimal adjustment or maintenance. Everything was designed for speed and ease of use, allowing workers with relatively limited training to achieve results that would require years of apprenticeship in German shipyards. Another devastating realization. American welding innovations didn't just make existing skilled welders faster. They made it possible to train new welders to acceptable proficiency in weeks rather than years. The bottleneck that constrained German production, the limited supply of master welders whose skills took years to develop, simply didn't exist in American shipyards. They had democratized expertise, turned a craft, requiring years of experience into a process that could be taught quickly and performed reliably by workers who had never touched a welding torch before Pearl Harbor. They passed a training area where a dozen new welders, identified by their awkward movements and frequent consultations with instructors, were practicing on scrap metal sections. Morrison gestured toward them with obvious satisfaction. Most of those folks started training 3 weeks ago. They'll be doing production work within another week or two. Not as fast as our experienced welders yet, but they'll get there. The new techniques are remarkably forgiving. Hard to screw up if you follow the basic procedures. 3 weeks of training to produce welders who would be doing actual production work. In Germany, a welding apprenticeship took 3 to 4 years before a worker was trusted with critical structural work. The Americans had compressed years of training into weeks through superior technique and equipment design. They had solved the human capital problem that constrained all industrial production, the problem of limited skilled labor, by engineering systems that reduced the skill requirements. Dietrich was conducting his own calculations, his lips moving silently as he worked through the mathematics. Finally, he turned to Müller and spoke quietly in German. If they're welding at 3 times our speed, and training welders in 1/10 the time we require, then their effective welding capacity is 30 times ours per capita. 30 times. With a larger population and more workers, the actual disparity is probably closer to 100 to 1 or more. 100 to 1. For every meter of welded seam Germany produced, America produced 100 meters. For every ship Germany launched, America launched 100 ships. The numbers seemed fantastical, impossible, the product of paranoid imagination rather than sober analysis. But the evidence was right in front of them, impossible to deny or dismiss. They reached the main assembly area, where complete hull sections were being joined into finished ships. The scale of operations was staggering. Massive cranes lifted hull sections weighing dozens of tons, positioning them with precision that suggested both excellent equipment and skilled operators. Welders swarmed over the joints where sections met, their torches creating a constellation of bright points in the industrial gloom. The noise was overwhelming, a thunderous symphony of metal on metal, hissing torches, shouting workers, and rumbling machinery. Morrison had to raise his voice to be heard over the din. "We're currently producing one Liberty ship every 42 days from keel laying to launch. That's averaged across all facilities. Some of our faster yards are doing it in less than 30 days. Richmond, California set the record last month, 14 days from keel to launch. Granted, that was a publicity stunt with extra workers and prefabricated sections, but it proved the concept. If we needed to, we could build ships that fast regularly. 14 days. From keel to launch. A Liberty ship displaced over 14,000 tons, fully loaded, measured 441 feet in length, carried 2,500 tons of cargo. German shipyards needed 6 months or more to build comparable vessels, and that was before Allied bombing disrupted production. The Americans were building equivalent ships in 1/10 the time, and treating 14-day construction as a publicity stunt rather than a standard operating procedure. Müller's mind kept returning to the welding. That was the key, the foundational innovation that made everything else possible. You couldn't build ships fast if joining the metal took months of careful work, but if you could weld quickly, reliably, with minimal skilled labor, then ship construction became an assembly process rather than a craft. Prefabricate sections in different locations, transport them to the shipyard, weld them together, launch the completed vessel. Simple, fast, scalable. The Americans had figured this out. They had invested in welding research, developed superior techniques, trained workers en masse, and transformed shipbuilding from a specialized craft into an industrial assembly process. And they had done it in less than 2 years, between Pearl Harbor and now, while simultaneously fighting a 2-ocean war and supplying half the world with military equipment. A young welder, a woman who looked barely 20 years old, was working on a seam near the viewing platform. Müller watched her with professional attention, looking for flaws, for signs of inadequate training or poor technique. He found nothing. Her movements were smooth, confident, economical. The weld bead she laid down was uniform, properly penetrated, textbook perfect. She completed a 12-foot seam in 4 minutes, inspected her work briefly, then moved to the next section without drama or fanfare. Just another routine task in a routine shift at a routine American shipyard. This young woman, with weeks of training, was out-welding German master craftsmen with decades of experience, not through superior skill or exceptional talent, through superior technique and equipment that made excellence achievable by ordinary workers with ordinary abilities. That was the American advantage distilled to its essence. They had engineered systems that allowed average workers to achieve extraordinary results. The implications extended far beyond shipbuilding. If Americans had developed revolutionary welding techniques for ships, they had certainly applied the same innovations to tank production, aircraft production, artillery production, bridge construction, building construction, everything involving steel. The welding advantage wasn't confined to one industry. It permeated the entire American economy, a foundational improvement that multiplied efficiency across every sector. Morrison led them to a quality control station, where completed welds were inspected using various testing methods: X-ray examination for critical structural welds, ultrasonic testing for detecting internal flaws, visual inspection for surface quality. The inspection protocols were rigorous, comprehensive, and apparently necessary because Morrison explained that rejection rates were remarkably low. "We're running about a 2% rejection rate on first-pass inspections," he said, consulting his clipboard again. That's down from 8% when we first implemented the new welding techniques. Workers have gotten better with practice, and we've refined the procedures based on field experience. The rejected welds are usually operator error rather than technique failure. Someone didn't follow the procedure correctly, or equipment malfunction, something like that. But overall, quality is excellent. These ships are holding up well in service. 2% rejection rate. German shipyards, using traditional welding methods and master craftsmen, typically saw rejection rates of 10 to 15% on first-pass inspections. The Americans, using revolutionary techniques and minimally trained workers, were achieving better quality control, superior speed and superior quality simultaneously. Not a trade-off where you sacrificed one for the other. Both improvements together, multiplying the advantage geometrically. Hauptmann Ernst Weber, a metallurgist from the Krupp Steelworks, had been examining the welded seams with intense concentration, running his fingers along the beads, looking for any sign of weakness or improper penetration. Finally, he spoke in German, his voice carrying resignation and professional admiration. "It's real. The welds are perfect. Better than perfect, actually. I don't understand how, but the metallurgy is sound. Whatever they're doing, it works." They moved to a different section of the shipyard, where tank sections were being fabricated for armoured vehicles. The same welding techniques were clearly in use here, with similar speed and efficiency. A tank hull that would require weeks of careful welding in German factories was being completed in days. The workers moved with practiced choreography, each person knowing exactly what needed to be done and when, never interfering with each other, never wasting motion or time. Müller noticed something else that increased his growing sense of despair. The American workers looked relaxed, almost casual in their competence. They weren't rushing, weren't frantic, weren't showing signs of the desperate urgency that characterized German war production. They worked steadily, efficiently, but without apparent stress. This wasn't an emergency mobilization pushed to its breaking point. This was normal operating procedure, sustainable indefinitely, with room to increase tempo if necessary. Morrison checked his watch. "We should head to the metallurgy laboratory. Dr. Harrison can explain the technical details of the welding innovations better than I can. He was one of the engineers who helped refine Meredith's original breakthrough into a production technique." The laboratory was a stark contrast to the industrial chaos of the shipyard floor. Clean, quiet, organized. It housed equipment for testing metal properties, analyzing weld structures, and researching new techniques. Dr. Thomas Harrison, a man in his early 50s wearing a white lab coat and thick glasses, greeted them with the enthusiasm of someone who loved his work and enjoyed explaining it to others. "Gentlemen," he began, "what you've seen today represents a fundamental rethinking of how we approach welding. The traditional method, which I assume you're familiar with, uses coated stick electrodes that burn down as you weld. Every few minutes, you have to stop, remove the stub, insert a new electrode, restart the arc, and continue. This start-stop process creates several problems. First, it's slow. Second, each restart risks introducing flaws at the junction point. Third, the frequent interruptions mean the metal undergoes multiple heating and cooling cycles, which can create internal stresses." He moved to a display showing various welding electrodes and equipment. James Meredith's insight was simple but revolutionary. What if we could eliminate the stops? What if the electrode could feed continuously, like thread through a sewing machine, allowing the welder to work without interruption? The technical challenges were significant. The electrode had to remain stable in the arc. The feeding mechanism had to be reliable and consistent. The flux composition had to protect the weld pool adequately without the thick coating used in stick electrodes. Harrison picked up a sample of the continuous feed electrode, a thin wire wound on a spool. This doesn't look revolutionary, but it represents about 18 months of intensive research and testing. The wire composition, the flux core, the feeding mechanism, all had to be engineered to work together perfectly. Once we figured it out, everything changed. A welder using this system can work continuously for minutes or even hours, limited only by fatigue rather than equipment constraints. Speed increased by a factor of 3 to 4. Quality improved because fewer starts and stops mean fewer opportunities for flaws. Training time decreased because the technique is actually easier to learn than traditional methods. He paused, looking at the German engineers with something approaching sympathy. I understand this must be shocking to witness, but I want you to understand something important. This innovation wasn't the result of some massive government program or enormous research facility. James Meredith was a working supervisor who got frustrated with inefficiency and decided to solve the problem himself. He did most of his experiments on his own time, using his own resources. That's the real strength of American industrial development. We have thousands of James Merediths, ordinary workers who see problems and figure out solutions, supported by a system that encourages rather than suppresses individual innovation. The words landed on Müller like hammer blows. The welding innovation wasn't some desperate wartime crash program. It was just Tuesday afternoon at an American shipyard, a routine example of the continuous improvement that characterized American industrial culture. And there were thousands more such innovations happening simultaneously across the economy, each one multiplying efficiency, each one widening the gap between American and German capabilities. They moved to testing stations where weld samples were being subjected to destructive testing to verify strength and quality. Harrison explained the protocols, showing stress test results, fatigue analysis, and metallurgical examinations. Every test confirmed what Müller already knew but still couldn't quite accept. The American welds weren't just faster, they were stronger, more reliable, more consistent than anything German industry could produce. One interesting discovery, Harrison continued, was that the continuous welding process actually produces stronger joints than traditional methods in many applications. The uninterrupted heat input creates a more uniform grain structure in the weld metal. Fewer starts and stops mean fewer stress concentration points. The result is that these ships, built in a fraction of the time using workers with minimal training, are actually more durable than vessels built using traditional methods. Speed, quality, and structural integrity all improved simultaneously. It was too much. Müller felt the foundations of his professional knowledge crumbling. Everything he had learned in 6 years of university engineering education, everything he had practiced in 15 years of industrial work, all of it was suddenly obsolete. Not wrong, not invalid, but simply surpassed by a superior approach that he hadn't even known was possible. Oberingenieur Hans Schmidt, who had been silent throughout most of the tour, finally spoke in German, his voice hollow with defeat. We've lost. Not eventually, not theoretically. We've already lost. We're fighting a war using industrial techniques from the last war, while the Americans have moved on to the next war's technology. We couldn't catch up if we had a decade. We have months at best. Morrison, not understanding German but picking up on the tone, offered what he probably intended as reassurance. This isn't meant to discourage you, gentlemen. The welding innovations will be shared internationally after the war. Modern industrial techniques benefit everyone when properly applied. But right now, at this moment, they're giving us a decisive advantage in war production. They would be shared after the war, as if that made it better. As if knowing that Germany would eventually get access to these techniques somehow compensated for the fact that by the time access came, Germany would be rubble, its cities destroyed, its industry devastated, its people starving. The Americans could afford to be generous because they had already won. The tour concluded with a return to the main shipyard floor. Müller watched the welders at work, their torches creating brief stars in the industrial darkness, each flash representing another few inches of welded seam, another small increment toward American victory. He thought about the German workers back home, skilled craftsmen working with outdated techniques, producing a fraction of what their American counterparts produced, believing they were doing their part for victory, even as that victory slipped further from reach with every passing day. Morrison shook hands with each German engineer, thanking them for their attention and professional interest. His courtesy was genuine, his manner friendly, without condescension or mockery. He didn't need to gloat. The facts spoke for themselves. As the Germans were loaded onto trucks for the return journey to the POW camp, Müller took one last look at the shipyard. 8 Liberty ships in various stages of construction. By this time next month, all 8 would be launched, replaced by 8 more, which would themselves be launched the month after. An endless production line of vessels, each one carrying supplies, weapons, and soldiers toward Germany's defeat. The mathematics were inescapable. If American welders worked 3 times faster than German welders, and if welding represented perhaps 30% of shipbuilding labor, then overall ship construction could be accelerated by a factor of at least 2, probably more when accounting for reduced training time and improved quality control. And that advantage extended across every industry, every factory, every production facility that used welding. Germany was being outwelded. It seemed almost absurd to phrase it that way, as if wars were won or lost based on the speed at which workers could join pieces of metal. But that was exactly what was happening. Industrial warfare came down to who could produce more equipment faster, and the side that could weld 3 times faster than their opponent had an insurmountable advantage. The trucks pulled away from the shipyard, carrying their cargo of defeated engineers back to Camp Patrick Henry, where they would spend the evening processing what they had witnessed. Some would refuse to believe it, insisting the demonstrations were propaganda designed to break their spirit. Some would accept it intellectually but not emotionally, maintaining hope through willful blindness to obvious truth. And some, like Müller, would understand completely and be crushed by that understanding. The camp library at Camp Patrick Henry was quiet on the evening of August 19, 1943. Friedrich Müller sat at a wooden table, a borrowed notebook open in front of him, trying to document what he had witnessed at the Newport News shipyard before the details faded or his mind began to rationalize them into something less devastating. Around him, a dozen other German engineers from the tour engaged in heated discussions. Their voices kept low to avoid disturbing other prisoners, but carrying an intensity born of professional crisis. "It's a trick," insisted Hauptmann Werner Vogel, an aircraft engineer from Messerschmitt. "They showed us their best workers, their fastest welders, under optimal conditions. You cannot extrapolate from carefully staged demonstrations to conclusions about their entire industrial capacity. It's propaganda, psychological warfare designed to break our morale." Müller didn't bother responding. He had filled 3 pages with calculations, cross-referencing what they had observed against known German production figures, projecting the implications across different industries. The numbers grew more horrifying with each calculation. Even if the Americans had shown them their best workers under optimal conditions, even if typical American welding speeds were only twice as fast as German speeds rather than 3 times faster, the strategic implications remained catastrophic. Dietrich, the U-boat engineer from Hamburg, sat beside Müller, reviewing his own notes. "I've been thinking about the training issue," he said quietly. "That might actually be more significant than the speed improvement itself. Germany has perhaps 10,000 master welders capable of critical structural work. We can't increase that number quickly because training takes years. The Americans can train adequate welders in weeks. That means they can scale up production simply by running more training programs. We can't match that no matter how many workers we try to train." The human capital constraint. Müller had been circling around the same realization. Wars between industrial powers came down to production capacity, but production capacity wasn't just about factories and raw materials. It was about skilled workers who could operate the machinery, perform the assembly, ensure the quality. Traditional industrial development assumed skilled labor as the bottleneck. You could build more factories, but you couldn't create more master craftsmen quickly. The Americans had solved that problem. Their welding technique was so forgiving, so easy to learn, that the skilled labor bottleneck simply vanished. They could train workers as fast as they could recruit them, limited only by the physical capacity of their training facilities. And since training took weeks rather than years, they could expand training capacity quickly by setting up more training centers. Germany couldn't compete with that. German industrial philosophy emphasized craftsmanship, extensive apprenticeships, traditional methods passed down through generations. It produced excellent results when you had time and stability. It collapsed when you needed rapid expansion during wartime mobilization. Americans had figured out how to achieve quality without craftsmanship, excellence without extensive training. They had engineered the human element out of the equation. Over the next several days, Müller became somewhat obsessed with understanding exactly how the American welding innovation worked. The camp library had technical journals, donated by various American industrial organizations as part of the prisoner education program. He spent hours searching through them, looking for any mention of welding innovations, continuous feed electrodes, or James Meredith. On August 23rd, he found it. A brief article in the June 1943 issue of Welding Engineer magazine, titled "Continuous Wire Feed Revolutionizes Production Welding." The article was only 4 pages long, written in accessible language for general technical audiences, but it contained enough detail to make Müller's engineering training useful for filling in the gaps. James Meredith wasn't a BRE, university-trained engineer. He had started as a welder's apprentice in 1928 at age 16, worked his way up through various positions, and had become welding supervisor at a small shipyard in Oakland, California in 1938. When war came and production demands exploded, Meredith found himself responsible for training hundreds of new welders to meet Navy contracts for cargo vessels. That's when he ran into the fundamental constraint. Traditional stick welding required too much skill for rapid training. New welders made mistakes, wasted materials, produced welds that failed inspection. The training bottleneck was killing his production schedule. So Meredith started experimenting. The article described his systematic approach. He began by analyzing exactly why stick welding was so difficult to master. The main issues were maintaining consistent arc length as the electrode burned down, managing the electrode angle correctly, knowing when to change electrodes, and restarting the arc smoothly. Experienced welders handled these challenges unconsciously through years of muscle memory. New welders struggled with all of them simultaneously. What if the electrode didn't burn down? What if it fed continuously from a spool, maintaining constant length? Then new welders wouldn't have to manage the changing electrode dynamics. They could focus on other aspects of proper technique. The arc would remain stable. The weld would be more consistent. The concept was simple. Implementation was not. Continuous feed welding had been attempted before, unsuccessfully. The technical challenges had always proven insurmountable. The electrode wire had to be the right composition to maintain a stable arc. It had to feed at exactly the right speed to match the burn rate. The flux protection had to be adequate without the thick coating used on stick electrodes. The feeding mechanism had to be reliable enough for production use. Previous attempts had failed on one or more of these requirements. Meredith spent 6 months experimenting, mostly on his own time, using scrap materials and borrowed equipment. He tried dozens of wire compositions, various flux formulations, different feeding mechanisms. Most failed. Some showed promise but weren't reliable enough. A few worked in laboratory conditions but broke down in actual production environments. Meredith developed a wire composition that used a tubular construction with flux contained inside the wire itself. The flux-cored wire provided protection as it burned, eliminating the need for external shielding gas in many applications. The feeding mechanism used a simple motor-driven roller system that maintained consistent wire speed with minimal complexity. The combination was reliable, easy to use, and dramatically faster than stick welding. Meredith's shipyard adopted the technique immediately. Productivity increased so dramatically that the Navy sent inspectors to verify the results, suspecting either fraud or quality problems. They found neither. The welds were excellent, the production rates real. By April 1942, the Navy was mandating adoption of continuous feed welding across all contracted shipyards. By summer, the technique had spread to tank production, aircraft manufacturing, and other industries. The article included some production statistics that made Müller feel physically ill. Average welding speed using traditional stick electrodes was approximately 3 to 4 inches per minute of completed weld for typical structural work. Continuous feed welding averaged 12 to 15 inches per minute for the same applications. Factor of 4 improvement in speed. Training time is reduced from months to weeks. Quality improved due to elimination of stop-start defects. The implications for ship production were spelled out clearly. A Liberty ship required approximately 15,000 linear feet of structural welding, not counting secondary welds. Using traditional methods with experienced welders, that represented about 600 hours of welding time. With continuous feed methods and less experienced workers, the same welding could be completed in about 150 hours. The welding bottleneck that had constrained ship production was eliminated. Müller set the journal down and stared at the wall. One man, one supervisor at a small shipyard, frustrated with training problems, experimenting in his spare time. 6 months of work, and he had developed an innovation that changed the course of the war, not through genius or exceptional brilliance, through systematic problem-solving and persistence. The article made it sound almost mundane, just another example of American industrial innovation, routine rather than revolutionary. That was perhaps the most frightening aspect. The Americans treated revolutionary innovations as routine developments. They had a system, a culture, an entire economy organized to encourage exactly this kind of innovation. Workers were expected to suggest improvements. Supervisors were evaluated on how well they implemented good ideas. Companies competed on innovation as much as price. The result was continuous incremental improvement across every industry, with occasional breakthrough innovations like Meredith's welding technique accelerating progress dramatically. Germany had nothing comparable. German industry was organized hierarchically, with decisions flowing from the top down. Engineers designed, workers assembled, managers supervised. Innovation came from universities and research institutes, not from shop floors. The idea that a welding supervisor with no university degree could revolutionize industrial production would have seemed absurd to German industrial leaders. They would have dismissed Meredith's innovations as the tinkering of an unqualified amateur, unsuitable for serious engineering consideration. And they would have been catastrophically wrong, just as they were wrong about so many other aspects of American industrial capacity. Müller spent the evening translating the article into German for the other engineers. They gathered in the library after dinner, perhaps 20 men with technical backgrounds, all trying to understand the scope of what they faced. He read the article aloud, translating as he went, then opened the floor for discussion. The initial reaction was denial, as he expected. Several engineers insisted the article must be propaganda, the results exaggerated, the technique flawed in ways not mentioned in a puff piece for popular consumption. But as the discussion continued, as the technical details were examined more carefully, the denials became less confident. Oberingenieur Gustav Richter, a welding specialist from the Krupp works who actually understood the metallurgy involved, asked the questions that mattered. What about porosity in the weld metal? Continuous. Feeding without adequate shielding should create gas pockets that weaken the joint. What about heat-affected zone properties? Continuous welding means sustained high temperatures that should cause grain growth and reduced strength. What about hydrogen embrittlement from moisture in the flux core? These are fundamental metallurgical issues that can't simply be wished away through clever feeding mechanisms. These were exactly the objections that had prevented continuous feed welding from succeeding in previous attempts. Müller had wondered about them himself. The article hadn't provided enough detail to answer fully, but it did mention that the flux core composition was proprietary and carefully engineered to address exactly these concerns. The Americans had apparently solved the metallurgical problems that had stymied earlier researchers. We need to assume they solved it, Müller said bluntly. We saw the results at the shipyard. Those welds were real, those ships were being built, at the claimed speeds. The quality control data showed low rejection rates. We can argue about how they solved the technical problems, but we can't deny that they did solve them. That's what matters strategically. The room fell silent as the implications settled over the group. They were educated men, trained engineers, knowledgeable about industrial processes. They understood what a fourfold improvement in welding speed meant for overall production capacity. They could do the calculations themselves, and those calculations all led to the same conclusion. Germany had already lost the industrial war. Not in the future, not eventually. The war was already over. decided by innovations like continuous feed welding that had transformed American production capacity beyond anything Germany could match or counter. Hauptmann Ernst Weber, the metallurgist from Krupp, finally voiced what everyone was thinking. Even if we learned about this technique today, even if we somehow obtained complete technical specifications and began implementing it immediately, we couldn't catch up. We lack the industrial infrastructure to retrain all our welders quickly. We lack the production capacity to manufacture the specialized wire and feeding equipment on the necessary scale. We lack the organizational flexibility to roll out major process changes across hundreds of factories. The Americans did all of this in 18 months, during wartime, while simultaneously expanding production across every industry. We couldn't match that in 5 years of peacetime, let alone during a war we're losing. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The welding innovation was just one example, but it represented something larger. American industrial culture was optimized for exactly this kind of rapid innovation and implementation. German industrial culture was optimized for precision, engineering, and quality craftsmanship. Both approaches had their merits in peacetime. In wartime, the American approach was decisively superior. Müller's thoughts turned to the man behind the innovation, James Meredith, welding supervisor, no university degree, motivated by practical frustration with training problems. He probably had no idea his experimentation would change naval construction worldwide. He was just trying to solve an immediate production problem at his shipyard. The fact that his solution had strategic implications was almost incidental. That was the American genius in miniature. They created systems where ordinary people solving ordinary problems occasionally produced extraordinary results, and they had millions of ordinary people, all empowered to experiment, innovate, and improve. Germany had a few thousand university-trained engineers and rigid hierarchies that discouraged innovation from below. The contrast couldn't be starker or more consequential. Over the following weeks, Müller continued researching American industrial innovations through the camp library's technical journals. What he found confirmed his worst fears. The welding breakthrough wasn't unique. American industry was generating similar innovations across every sector. In aircraft production, new assembly techniques reduced manufacturing time for a B-17 bomber from 40,000 man-hours to 18,000 man-hours between 1941 and 1943, not through harder work or longer hours, through better methods, improved tools, and systematic elimination of wasted effort. In artillery production, new manufacturing processes allowed production of the 75mm anti-aircraft gun to increase from 200 units monthly in early 1942 to over 1,000 units monthly by late 1943. Same factories, same workers, better processes. In tank production, the introduction of modular assembly and simplified design reduced production time for an M4 Sherman from 9,000 man-hours to 4,000 man-hours. The Sherman wasn't the best tank in the war from a pure performance standpoint, but it could be produced more than twice as fast as a German Panzer IV and nearly 4 times faster than a Tiger. Quantity had a quality all its own when the production disparity was that extreme. The pattern repeated across every industry. American production wasn't just larger in scale, it was more efficient per worker, more innovative in methods, more flexible in implementation. They were fighting a different kind of war, one where industrial efficiency mattered more than tactical brilliance or operational excellence. Müller started compiling what he called his Book of Defeat, a detailed analysis of why Germany was losing the war from an industrial perspective. The welding innovation was Chapter 3, following chapters on American steel production and aluminum manufacturing. By September, he had drafted 11 chapters, each one documenting a different aspect of American industrial superiority, each one reinforcing the same conclusion. Germany never had a chance. The war was lost before it began, lost in the decades of industrial development that gave America overwhelming advantages in production capacity, innovation capability, and resource access. Military skill and tactical excellence could win battles. They couldn't overcome a 3-to-1 or 4-to-1 or 5-to-1 disadvantage in equipment production. On September 14th, Müller was granted permission to send a heavily censored letter to his wife in Berlin. The censors would remove anything of military significance, but he could share general observations about his treatment and conditions. He wrote carefully, knowing she would read between the lines. "The Americans are treating us well," he wrote, "better than we probably deserve. I have learned much here about industrial methods and technical processes. It has given me a new perspective on many things. When this war ends, and it will end soon, Germany will need to rebuild everything, not just our cities and factories, but our entire approach to industrial organization. The Americans have much to teach us about efficiency and innovation. I hope we will be willing to learn." His wife would understand. She knew him well enough to recognize despair beneath diplomatic phrasing. She would know that "the war will end soon" meant Germany was losing. She would understand that "new perspective" meant his worldview had been shattered. She would recognize that "willing to learn" meant Germany had been wrong about fundamental assumptions. The letter was returned to him 3 days later, with most of it crossed out by censors. Only 2 sentences remained. "The Americans are treating us well. I hope to return home when circumstances permit." Everything else was too revealing, too demoralizing, too honest about German defeat. On October 2nd, another tour was organized, this time to a tank manufacturing facility in Detroit. Müller volunteered immediately, eager to see whether the welding innovations had been applied to armored vehicle production. 12 German officers were selected, all with engineering or technical backgrounds, loaded onto a train and transported north under guard. The Fisher body tank arsenal sprawled across 600 acres of Detroit industrial landscape. Before the war, Fisher Body had manufactured automobile bodies for General Motors. When war came, they converted to tank production using the same mass production techniques that had made American automobiles affordable for middle-class families. The tour guide was a woman, which initially shocked the German visitors. Ingrid Hansen was production engineer, a title that would have been impossible for a woman to hold in Germany, explaining tank assembly processes with competence and confidence that made it clear she knew exactly what she was talking about. She had started as an assembly line worker in 1942, shown aptitude for technical work, received engineering training through a company program, and been promoted to her current position based on merit. The Germans followed her through the facility, watching welders, many of them also women, using continuous feed techniques to assemble tank hulls at speeds that would have been impossible using traditional methods. The welding workstations were ergonomically designed for maximum efficiency. The wire feeding systems were compact and mobile. Quality control was built into the process rather than added afterward. Everything was optimized for speed and reliability. "We're currently producing an M4 Sherman every 45 minutes, Hansen explained, her voice carrying over the industrial noise. "That's averaged across 3 shifts, 7 days per week. Monthly production runs about 1,200 tanks from this facility alone. Similar production rates are being achieved at Chrysler's tank, arsenal, and other facilities. Combined production exceeds 3,000 tanks monthly across all manufacturers." 3,000 tanks monthly. Müller did quick calculations. Germany was producing perhaps 600 tanks monthly from all factories combined, and that was counting all types, from light reconnaissance tanks to heavy Tigers. The Americans were producing 5 times as many tanks, and the production gap was widening as American factories refined their processes and German factories were disrupted by Allied bombing. But raw numbers told only part of the story. The M4 Sherman wasn't as heavily armoured as a Tiger or as well armed as a Panther. German tankers had tactical advantages in individual engagements, but the Sherman was reliable, easy to maintain, adequately armed for most situations, and produced in overwhelming numbers. For every Tiger Germany produced, America produced 40 Shermans. You could lose 39 Shermans destroying a Tiger and still come out ahead. The Germans had optimized for quality. The Americans had optimized for quantity. In a war of attrition, quantity won, especially when quality was adequate rather than poor. They stopped at a welding station where a young woman, probably 22 or 23 years old, was welding the final seams on a tank hull. Her movements were confident, practiced, economical. The weld bead was uniform and clean. She completed the seam, shut down her torch, inspected her work briefly, then marked the hull as ready for next station. The entire process took 11 minutes for a welding job that would have required 40 minutes using stick welding. Hansen noticed the German's interest. "That's Margaret O'Connor. She's been welding for 9 months, started training last December. She's one of our faster workers, but not exceptional. We have about 400 welders with similar skill levels working across all shifts. The continuous feed technique makes training so much faster that we can maintain full staffing, even with the high turnover common in war industries." 9 months of welding experience. In Germany, she would still be considered an apprentice, years away from being trusted with critical structural work. Here, she was producing tank hulls that would be shipped to Europe and Africa within weeks, engaging German tanks whose welders had decades of experience. And she was beating them, not through superior skill, but through superior technique and equipment. The Americans had engineered individual expertise out of the equation, creating processes that allowed ordinary workers with minimal training to achieve results that would require master craftsmen using traditional methods. Oberingenieur Stefan Koch, who had managed tank production at Mahn in Nuremberg, asked the question they were all wondering: "What is your rejection rate for welded hull sections?" Hansen checked a clipboard she carried. "Currently running about 1.3% for critical structural welds. Most rejections are operator error rather than process failure, workers who don't follow procedures correctly or equipment malfunctions. Overall, quality is excellent and getting better as workers gain experience, and we refine the techniques." 1.3%. German tank production, using master welders and traditional techniques, typically saw rejection rates of 8 to 12% on hull welds. The Americans, using minimally trained workers and revolutionary techniques, were achieving better quality at 4 times the speed. The tour continued through the assembly line where completed hulls received engines, transmissions, tracks, and weapons. Everything was modular, designed for rapid assembly by workers with limited specialized knowledge. A complete tank could be assembled from major components in less than 2 hours, a process that would take days in German factories where tanks were still assembled more like custom machinery than mass-produced goods. They reached a testing area where completed tanks underwent final inspection and operational checks. Engines were started, transmissions tested, weapons systems verified. Tanks that passed inspection, roughly 98%, were driven onto transport trains for shipment to ports and eventual deployment overseas. The entire process, from raw steel to completed tank ready for combat, took approximately 6 weeks at this facility. German tank production required 5 to 6 months from start to finish, assuming no delays from material shortages or bombing disruptions. The Americans were building tanks 4 times faster, while also building them in vastly greater numbers. The production advantage was crushing, unsurvivable, decisive. As the tour concluded, Hansen offered a final observation that hit Müller with the force of revelation. "The welding innovation was really the key to everything you've seen today. Before we solved the welding bottleneck, we couldn't mass-produce armored vehicles efficiently. Welding was too slow, required too much skill, created too many quality problems. Once that was solved, everything else became possible. Tank production went from craft work to assembly line manufacturing. That's when production really exploded. One innovation, one welding supervisor solving a training problem, and it had transformed the entire industrial landscape, making mass production of complex armored vehicles possible at scales previously unimaginable. The ride back to camp was silent, each German lost in his own thoughts, processing implications that grew more overwhelming the more deeply they were considered. Müller stared out the train window at the American landscape rolling past. Factories, farms, towns, all intact, untouched by war, operating at full capacity. While German cities burned, German factories were bombed, German infrastructure crumbled, America built, produced, innovated. That evening in the camp library, Müller, added a new section to his book of defeat. He titled it The Welding Revolution and Its Consequences. He tried to capture not just the technical details, but the deeper implications about industrial culture, organizational flexibility, and the systematic advantages that made American production so overwhelmingly superior. Germany lost this war in February 1942, he wrote, when a welding supervisor in Oakland, California, figured out how to make electrodes feed continuously. We just didn't know it yet. By the time we understood what had happened, American shipyards were producing 4 times as many ships, American tank factories were producing 5 times as many tanks, and American industrial capacity had been multiplied across every sector. No amount of tactical brilliance or operational excellence could overcome such fundamental industrial advantages. We were defeated by innovation we didn't even know existed. He paused, then added a final observation. Lesson isn't about welding techniques or production methods. It's about systems that encourage innovation at every level, from shop floor to executive suite. America created such a system, Germany did not. That difference, more than any other factor, determined the war's outcome before the first shot was fired. Industrial wars are won by whoever can innovate faster, implement better, and scale more quickly. America possessed all 3 advantages. Germany possessed none. The defeat was inevitable. The winter of 1943 brought increasingly grim news from the Eastern Front and growing Allied air superiority over Germany. In Camp Patrick Henry, Friedrich Müller continued his documentation project, filling notebook after notebook with technical analysis of American industrial methods. But his focus kept returning to the welding innovation, the single breakthrough that seemed to encapsulate everything about why Germany was losing. In late November, Müller learned that the camp would be hosting a special visitor. James Meredith himself, the welding supervisor whose experiments had revolutionized American production, was coming to speak as part of the prisoner education program. The Americans apparently saw value in showing German engineers the human face behind the industrial innovations they had witnessed. December 8, 1943. Müller and 37 other German engineers gathered in the camp's recreation hall, unsure what to expect. Meredith arrived without fanfare, a compact man in his early 30s wearing a simple work shirt and slacks, looking more like a factory worker than the man who had changed the course of the war. He carried a battered briefcase containing samples and diagrams. "Gentlemen," he began, speaking through a translator, "I understand you've seen the results of some welding techniques I developed. I wanted to explain how it happened, not because I'm proud, though I am, but because I think it illustrates something important about how American industry approaches problems." He set up a small demonstration on a table at the front of the room. Sample electrodes, both traditional stick types and his continuous feed wire. A simple feeding mechanism he had built himself during his early experiments. Photographs of failed attempts, broken equipment, welds that didn't work. "I'm not an engineer," Meredith continued. "I have a high school education and 15 years of welding experience. When I started experimenting with continuous feeding, I didn't know it was supposed to be impossible. I just knew that training new welders was taking too long, and I needed a better solution." He explained his systematic approach. How he had analyzed the learning curve for traditional welding, identified which skills were hardest to master, focused on eliminating or simplifying those specific challenges. The continuous feeding solved the hardest problem, maintaining consistent arc length, which allowed new welders to focus on other aspects of proper technique. "I failed more than I succeeded," Meredith said with a slight smile. "For every wire composition that worked, I tried 10 that didn't. For every feeding mechanism that was reliable, I built 5 that broke down constantly. The breakthrough wasn't genius. It was persistence and systematic experimentation." Müller watched this unremarkable man explain how he had casually revolutionized industrial production and felt something close to despair. In Germany, such innovation would have required approval from multiple levels of management, review by university-educated engineers, testing at official research facilities. The process would have taken years if it happened at all. More likely, it would have been rejected as unworkable or unnecessary. Meredith had simply started experimenting in his spare time, using his own resources, driven by practical frustration rather than theoretical interest. When he found something that worked, his supervisors recognized its value immediately and helped him refine it for production use. Within months, it was being implemented across the industry. The entire cycle from problem identification to widespread implementation took less than a year. "The real credit belongs to the system," Meredith said, addressing a question about whether he felt proud of his achievement. "I work for a company that encourages workers to suggest improvements. I have supervisors who listen to ideas from the shop floor. I operate in an industry that rewards innovation and quickly adopts better methods. I just happen to be the guy who figured out this particular solution. If I hadn't, someone else would have, eventually." That was the American advantage distilled to its purest form, a system that encouraged thousands of potential innovators, supported their experiments, rapidly implemented successful solutions, and moved on to the next problem. Germany had a system that centralized innovation in ICOPA. Universities and research institutes required extensive approval for changes, moved slowly in implementation, and discouraged initiative from below. Both systems could produce innovations. The American system produced them faster, implemented them more quickly, and scaled them more effectively. In peacetime, the difference might not matter. In wartime, it was decisive. After the presentation, Meredith invited questions. The Germans asked about technical details, metallurgical properties, implementation challenges. He answered patiently, honestly, acknowledging problems and limitations. His technique wasn't perfect. It didn't work for all applications. Traditional welding still had its place, but for production welding, the kind that built ships and tanks and aircraft, continuous feeding was simply superior. Hauptmann Koch, the tank production manager, asked the question that was on everyone's mind. "Did you realize, when you developed this technique, that it would have such strategic significance?" Meredith paused, considering carefully. "Not at first. I was focused on my immediate problem, training welders fast enough to meet production schedules. But as we saw the results, as production rates increased and the technique spread to other industries, yes, I began to understand the larger implications. That's been humbling, honestly. I set out to solve a training problem. I ended up contributing to winning the war." The meeting concluded with Meredith shaking hands with each German engineer, a gesture of professional respect that transcended the context of their meeting. Müller shook his hand and said through the translator, "You have achieved something remarkable. I hope you understand the significance of what you accomplished." Meredith nodded. "I do now. Thank you." As the Germans filed out, Müller felt a strange mixture of admiration and grief. Admiration for the achievement itself, for the systematic problem-solving and practical innovation that characterized American industrial culture. Grief for what it represented about German defeat, about how thoroughly Germany had been outmatched not just in resources, but in the fundamental organization of industrial society. The months that followed brought confirmation of everything Müller had concluded. D-Day demonstrated the American ability to project overwhelming force across an ocean, supported by ships built with revolutionary welding techniques. The advance across France showed American armor superiority through sheer numbers, tanks produced using mass production methods. The bombing campaign intensified, using aircraft built in factories that could manufacture them faster than Germany could shoot them down. By spring of 1944, even the most optimistic German prisoners acknowledged that defeat was inevitable. The only question was how long it would take and how much additional destruction Germany would suffer before accepting surrender. Müller's documentation project evolved, from technical analysis into something more like historical record. He wanted future generations to understand not just that Germany lost, but why. The welding innovation was emblematic of larger patterns, of systematic advantages that made American victory inevitable once industrial mobilization fully engaged. In August 1944, nearly a year after his first visit to the Newport News shipyard, Müller was granted permission to send another letter home. The censors were more lenient now, with German defeat obvious to everyone. He wrote to his wife about what he had learned. "The war has taught me that nations succeed not through force or ideology, but through systems that allow ordinary people to achieve extraordinary things. The Americans have built such systems. Germany did not. That difference, more than any battle or campaign, determined the outcome. When this is over, when we rebuild, we must remember these lessons. We must create a society that encourages innovation, rewards merit, and allows people at every level to contribute their best. That is the only path forward." The letter arrived in Berlin 3 months later, delivered to an apartment building that had been partially destroyed by bombing. His wife read it in a cold room with no electricity, understanding that her husband was describing not just German military defeat, but the intellectual and philosophical bankruptcy of the system that had led Germany into a catastrophic war. Victory in Europe came in May 1945. Friedrich Müller was repatriated to Germany in November, returning to a country physically devastated and psychologically shattered, but he carried with him detailed documentation of American industrial methods and a clear understanding of what Germany needed to change. In the decades that followed, the lessons learned in American POW camps influenced German industrial reconstruction. The Federal Republic of Germany embraced democratic institutions, market, economics, and industrial practices that encouraged innovation at all levels. The continuous feed welding technique that had helped defeat Germany became standard practice in German shipyards and factories, part of the technological transfer that accompanied reconstruction. James Meredith continued working in the welding industry after the war, eventually starting his own consulting firm that helped companies implement modern welding techniques. He gave occasional lectures at engineering schools, always emphasizing that innovation came from practical problem-solving rather than theoretical brilliance. He died in 1978, having lived long enough to see his wartime innovation become standard practice worldwide. The welding revolution that began in a small Oakland shipyard in 1942 transformed global manufacturing. By the 1950s, continuous feed welding was used in virtually every industrialized nation. The technique continued evolving, with improvements in wire composition, feeding mechanisms, and automation. Modern robotic welding systems still use principles that Meredith pioneered, adapted and refined by generations of subsequent innovation. The strategic lesson remained relevant long after World War II ended. Industrial wars are won by whoever can produce equipment faster and more efficiently. Tactical excellence and operational skill matter, but they cannot overcome overwhelming industrial disadvantages. Nations that encourage innovation, implement improvements quickly, and organize production efficiently will defeat nations that do not, regardless of other factors. For Friedrich Müller, the welding innovation remained a defining memory. In his later years, working as a consultant helping rebuild German industry, he often told the story of watching American welders work at speeds he had thought impossible, creating joints stronger than anything German craftsmen could produce, using techniques developed by a supervisor with no engineering degree. "That was when I understood we had lost," he would say. "Not when we surrendered, not when Berlin fell, but when I watched a young American woman with 9 months of training outweld German masters with decades of experience. The war was decided by innovations we didn't know existed, implemented by a system we couldn't match. Everything after that was just playing out the inevitable conclusion." The timer that German engineers refused to believe in 1943 became the standard by which all industrial welding was measured. What had seemed impossible became routine, then obsolete, as further innovations continued improving the process. The revolution that James Meredith started never really ended. It just became the new baseline from which the next generation of innovations would emerge. That, perhaps, was the final lesson. Industrial progress never stops. Nations that embrace continuous improvement, that encourage innovation at every level, that implement better methods quickly, those nations will prosper. Nations that resist change, that centralize innovation, that move slowly in adoption, those nations will fall behind. Germany learned that lesson through devastating defeat. The knowledge, purchased at terrible cost, became part of the foundation for post-war reconstruction and eventual prosperity. The welding technique that helped defeat Germany became part of the industrial base that made the German economic miracle possible. In the end, industrial warfare wasn't really about which side had better weapons or braver soldiers. It was about which side could innovate faster, produce more efficiently, and implement improvements more quickly. America possessed all those advantages. Germany possessed none. The outcome was never in doubt, decided by a welding supervisor's experiments in early 1942, long before most people realized the war's trajectory had already been determined. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.